Hi, and welcome back. If you have reached so far in this journey through the thermodynamics of mixtures, you are certainly motivated, and you deserve the paybacks that these and the next lesson are going to give you. Here we start talking of activity coefficients in liquid mixtures. That will bring us fully into the world of mixtures and to understanding how to deal thermodynamically with individual components that get together and mix up, such as the individual oxides that form a silicate melt. We will therefore get to the core of mixture thermodynamics. Understanding activity coefficients and their relationships with other thermodynamic quantities, first of all, gives energy. And modeling the activity coefficient of volatiles dissolved in silicate melts will take 2 lessons. This is in fact identified as part 1, as you can read in the title at the bottom of this slide. There will be, therefore, a part 2, at the end of which our journey through the development of a fully real thermodynamic model of multi-component volatile equilibrium in silicate melts will be concluded. After that, you will start exercising with SolveCAD, a numerical code that solves the whole system of equations that we have been and will be developing step after step. And what's most important, you will have acquired sufficient knowledge to develop yourself the next level thermodynamic model of mixtures as complex as silicate melts. We saw in the previous lessons how to model the fugacity coefficient for volatile components in the gas phase and the reference fugacity for the volatile components in the liquid phase. The activity coefficient is the last term necessary to complete our real multi-component gas melt equilibrium modeling. First of all, let's start by recalling where and how the activity coefficient appeared in our equilibrium equations. That happened in lesson 3 under unit 1, and it followed from just definitions. We defined the activity of a component in a mixture as the ratio between its fugacity and some reference fugacity. We have dedicated the entire lesson 6 to model the reference fugacity for volatiles dissolved in a melt. And we defined the activity coefficient of a component as the ratio between its activity and mole fraction. Then, by simply recasting these definitions, we obtained an expression for the fugacity of a component in a mixture that we said it is often employed for components in the liquid phase. That makes up nearly all of what we have said till now about the activity coefficient. Besides that, we state that the activity coefficient and the reference fugacity are intimately related. In fact, while the latter, the reference fugacity, defines a reference for the computation of fugacity, the activity coefficient tells us what is the deviation from that reference as due to the difference between current and reference conditions. Reference fugacity and activity coefficient distribute among themselves the job of defining the fugacity of a component in a mixture. In our modeling of the reference fugacity, we say that a convenient choice is that of giving it the job of minding at the roles of pressure and temperature in defining fugacity, while the role of melt composition is ascribed to the activity coefficient. That is exactly what we need to develop in this and the next lesson, how to express the activity coefficient and its dependence on melt composition. To do so, let's start from the Gibbs energy. As you know, we always start from the Gibbs energy, which embeds the first and second laws of thermodynamics, and it conveniently expresses the change of energy of a system in terms of pressure and temperature changes. We know from lesson 1 that chemical equilibrium is achieved when the Gibbs energy is minimized, because that corresponds to maximizing system entropy as required by the second law. Gibbs energy is central in the definition of chemical equilibrium. Let's therefore concentrate on Gibbs energy and delay the activity coefficient to a few slides forward. We will see the activity coefficient emerging in our reasoning in a way that fully clarifies its relationships with the Gibbs energy, as well as its role, meaning, and relevance in chemical equilibrium. Let's start by noticing, once again, that the Gibbs energy is defined in terms of volume and entropy. We are dealing with mixtures, so we need to consider the volume and entropy of mixtures. In order to understand the Gibbs energy of mixtures, the fundamental question is therefore this one. What happens to volume and entropy when different components mix up, giving origin to a mixture? For example, when silica, alumina, and so on, including dissolved volatiles, mix up in a silicate melt. In general, when we mix up components, the volume of the resulting mixture will be similar to the sum of the volume of all components, but not identical to it. When we measure the mixture volume, we find differences from the simple sum of the volumes of the components. What's the origin of those differences? Differences between the volume of the mixture and the sum of the volume of its components arise because the components can interact with each other, and these interactions may have relevant consequences, such as, for example, the creation of new bonding and new molecular structures, like those that we reconstruct from spectroscopic analysis of silicate melts. In general, interactions between the different components can be described in terms of attractive and repulsive forces, which result in effective contraction or expansion of the mixture with respect to the simple sum of the volumes of its constituents. The difference between the mixture volume and the sum of the volumes of its individual components is called the excess volume, indicated here with a superscript E. For ideal mixture, the excess volume is zero, meaning that in ideal mixtures, the components are like inert objects that do not interact with each other, so that the mixture volume is simply equal to the sum of the volumes of the individual components. The excess volume is therefore due to the real behavior of a mixture, whereby its components are chemically reactive species interacting with each other and giving rise to attractive and repulsive forces. The situation with entropy is similar but different. We still have the sum of the entropies of all components, and we have an excess entropy deriving from the interactions between the components. However, we will see in a moment that with entropy, there is a further term that we call the ideal mixing term. To understand what is the origin of this term, we need to consider entropy a bit more. There are truly hundreds or thousands books dealing with the single quantity entropy, providing explanations and interpretations of it. That is because of the so singular qualities of entropy that I briefly recalled in lesson 1. Among such qualities, entropy is the only physical quantity which gives a direction to time. We don't explore the wonders of entropy in this lesson, those that contributed to convince some of the greatest scientists, including Albert Einstein, that thermodynamics is the more fundamental of all sciences. Let's instead just benefit here from the work of one of the greatest scientists ever, the Austrian Ludwig Boltzmann, who was the father of statistical thermodynamics. Boltzmann was the first to understand the relationships between the macroscopic description embedded in classical thermodynamics and the microscopic world of atoms and molecules. In particular, he understood that entropy is in fact a measure of the number of microscopic configurations that correspond to a given macroscopic state. This was a so big achievement that the corresponding equation appears on Boltzmann's gravestone in Vienna. To understand it, let's go one slide back and consider a very simple idealization that's made of just two constituents which can be arranged only along a line and at a fixed distance. Consider the case where the two constituents are the same by any respect. Say they are both yellow balls with same size, and that makes all of their properties. Because the two balls are identical by any respect, there is no distinction between the microscopic states where one of the two is placed on the left or on the right. In other words, the macroscopic system made of the two yellow balls would have one and only one possible microscopic configuration. Because entropy measures the number of microscopic configurations that correspond to a given macroscopic state of a system, the entropy of our system made of the two similar yellow balls will be 1. Now, let's consider the case where the two balls can be distinguished for some respect. Say, one is yellow while the other one is red. In such a case, the two situations where the red ball is placed to the left or to the right are distinguished. The macroscopic system made of one yellow and one red ball now has two possible microscopic configurations. Therefore, the entropy of this ecosystem is 2. Let's consider it further. The second system shows an increase in entropy with respect to the first system due to the simple fact that the components are different from each other. That is not due to any attractive or repulsive interaction between the components. Rather, it is due to the simple fact that the components are different and can be distinguished from each other. In other words, when putting different components together, there is a surplus of entropy simply because of the different nature of the component themselves. We call this surplus the entropy of ideal mixing. Therefore, different from volume, the entropy of mixing is in general constituted by 3 terms. The term, which represents the sum of the entropies of the individual components. A term which arises because of attractive, repulsive forces and real behavior of the mixture. And similarly to the excess volume, it is called the excess entropy, and a term that does not exist in the case of volume and which represents a surplus of entropy simply due to putting together different components. Once again, this term is an ideal mixing term, meaning that it is not related to any attractive or repulsive forces between the components. Even if the component mix ideally, the ideal mixing entropy term arises, and that's the reason why it brings the term ideal in its name. Just because the different nature of the components in the mixture increases the number of microscopic states that correspond to a given macroscopic state of the system. In summary, when we take individual components and mix them up to form a mixture, the resulting volume is described by two terms, one which represents the sum of the individual volumes of the components, and the other one, the excess volume, which is due to attractive repulsive forces between the mixture components. Whereas the mixture entropy is described by three terms, two of them being equivalent to the terms making up mixture volume, and the third one being exclusive of entropy, represented by the entropy of ideal mixing, and due to simply putting together components that are distinguished one from the other. Now, let's go back to mixture Gibbs energy, which depends on mixture volume and mixture entropy. We know now how to express, in general terms, the mixture volume and mixture entropy as a summation of the terms reported here. Because volume is the derivative of Gibbs energy at constant temperature, and entropy is minus the derivative of Gibbs energy at constant pressure, it follows that, in general, the Gibbs energy of a mixture is also a summation of terms, such that, when partially derived in pressure, it gives the expression for mixture volume, and when partially derived in temperature, it gives the expression for mixture entropy. Thus, the Gibbs energy of a mixture is the sum of three terms. The first term is the summation of the individual Gibbs energy of the components. When partially derived in pressure, this becomes the summation of the individual volumes of the components. And when partially derived in temperature, it becomes minus the summation of the individual entropies of the components. More in detail, and recalling that molar Gibbs energy is chemical potential, this term involves the summation of the chemical potential of the individual components, each multiplied by the corresponding number of moles. The second term in the expression of Gibbs energy is the Gibbs energy of ideal mixing. This term must depend on temperature, and it must be independent from pressure, so that when partially derived in temperature, it gives minus the entropy of ideal mixing, and when partially derived in pressure, it gives 0. Finally, the third term in the expression of the Gibbs energy is the excess Gibbs free energy, which, upon partial derivation, gives rise to excess volume and to excess entropy. Of course, excess volume when partially derived in pressure, and minus excess entropy when partially derived in temperature. Here is the same general expression for the Gibbs energy of mixing. We need now to find an expression for the Gibbs energy of ideal mixing. The reason for that will be evident in the following, where we will finally relate the Gibbs energy to the activity coefficient. How can we express the Gibbs energy of ideal mixing? We know that it's only a function of temperature, as its partial temperature derivative relates to entropy of ideal mixing, while its partial pressure derivative is 0. But What is an expression for heat? Here is another exercise for you. As for the previous exercises, you can either try to solve it or skip it and continue with the presentation. In both cases, you will see the solution in the following. The exercise is this one. Find an expression for the Gibbs energy of ideal mixing. There is a suggestion for it. Just start with individual ideal components. Then consider them as mixed ideally to originate an ideal mixture. The Gibbs energy of ideal mixing is simply the difference between the final and the initial Gibbs energies. Press pause now if you want to do the exercise. Okay, in order to find an expression for the Gibbs energy of ideal mixing, let's refer to an ideal mixing process. Ideal mixing implies that any excess term deriving from mixing the components is equal to 0. Because the excess terms are 0, the only difference between the Gibbs energy of the mixture and the sum of the Gibbs energies of the individual components is equal to the Gibbs energy of ideal mixing. Therefore, the difference between the Gibbs energy of the ideal mixture and the sum of the Gibbs energies of the ideal components will give us the Gibbs energy of ideal mixing that we are looking for. For the individual components, let's write the sum of their Gibbs energies. Because we are dealing with pure components, their individual Gibbs energies correspond to the individual chemical potentials, each multiplied by the number of moles of the corresponding component. We can then write the chemical potential in terms of fugacity. And because we are dealing with pure components at ideal conditions, fugacity and pressure coincide, and we can therefore substitute fugacities with pressures. For the ideal mixture, the reasoning is similar. The Gibbs energy is still expressed in terms of chemical potentials, still at ideal conditions. But now we are referring to a mixture. Therefore, the fugacity of each component is no more equal to pressure. Rather, it corresponds to the partial pressure of the component. Now, as we said, simply write the Gibbs energy of ideal mixing as the difference between the Gibbs energy of the ideal mixture and the sum of the Gibbs energies of the ideal components, what we have in the second equation minus what we have in the first equation. For all components, either as individual or in a mixture, we can choose the same reference pressure. The resulting expression for the Gibbs energy of ideal mixing, obtained by subtracting the Gibbs energy of the ideal components from the Gibbs energy of the ideal mixture, is this one. For each term in the summation, that is, for each component in the mixture, we can further replace the number of moles with the total number of moles constituting the mixture times the mole fraction of the component. We finally obtain the general expression for the Gibbs energy of ideal mixing. As expected, it is only a function of temperature. Therefore, it gives rise to an entropy of ideal mixing, while there is nothing such as a volume of ideal mixing, because this term becomes 0 upon partial derivation in pressure. Note one relevant aspect emerging from the expression for the Gibbs energy of ideal mixing. The mole fractions in the logarithmic terms are less than 1 by definition. Therefore, the logarithmic terms are all negative, and as a consequence, the Gibbs energy of ideal mixing is also negative. There is no other term representing the difference between the Gibbs energy of ideal components and the Gibbs energy of the ideal mixture. That means that the Gibbs energy of an ideal mixture is always less than the sum of the Gibbs energies of the individual ideal components. As a consequence, ideal components forming an ideal mixture spontaneously mix, because that results in a decrease of the Gibbs energy of the system. That indeed matches our experience. Most gases at atmospheric conditions behave not far from ideal, and so do their mixtures. Accordingly, and as predicted by the Gibbs energy of ideal mixing that we have just defined, gases at atmospheric conditions tend to mix spontaneously, and we now know the reason why. Well, now we are able to write a more complete expression for the Gibbs energy of mixing, as we know how to represent the reference term given by the contribution of the individual components and the ideal mixing term related to the entropy increase due to ideal mixing. On the contrary, we haven't said much about the excess term. Besides that, it embeds any deviation from ideal behavior due to attractive repulsive forces between the components in the mixture. We will explore the excess Gibbs energy term more in the next lesson. Now we see how this expression leads us to understand much more about the activity coefficient, which is, in fact, the objective of this lesson. We start by recalling that the chemical potential of a component in a mixture is equal to the partial molar Gibbs energy of that component in the mixture, given by partially deriving the Gibbs energy in the number of moles of the component. We can therefore apply this expression to the expression of the Gibbs energy on top and obtain a new expression for the chemical potential of a component in a mixture. This turns out to be given by the chemical potential of the individual component, here indicated with a 0 at the apex, plus a term which embeds the contribution of that component to the ideal entropy of mixing, plus a third term which is simply the partial molar excess Gibbs energy of the component, or in other words, the contribution of the component to the excess Gibbs energy. We know from lesson 3 that the chemical potential of a component in a mixture is also given by this other expression, mu equal to mu0 plus RT logarithm of the activity. The activity of a component in a mixture is equal to the product of its mole fraction and its activity coefficient. Therefore, we can expand into mu equal to mu0 times RT logarithm of xi, the mole fraction of component I, times RT plus RT logarithm of gamma I, the activity coefficient of component I. The comparison between the two expressions for the chemical potential allows us to finally describe the activity coefficient of a component in a mixture as the partial molar excess Gibbs energy of that component in the mixture. In other words, the activity coefficient of a component tells us how the excess Gibbs energy of the mixture varies when small bits of that component are added to or they are removed from the mixture. Let's consider it further. Assume a given component in a mixture has an activity coefficient less than 1. Thus, the left-hand side of the equation at the bottom of this slide is negative, meaning that adding a small bit of that component to the mixture results in a decrease of the excess Gibbs energy of the mixture. That works in favor of dissolution of the component in the mixture. Careful, it doesn't mean that the component will be dissolved, as that relates to the change of the total Gibbs energy and not only of its excess part. But the non-ideal contribution due to the attractive repulsive forces generated by the addition of the component to the mixture and represented by the excess Gibbs energy will be in favor of this solution. We are now able to fully understand a lot of things, including the meaning of ideal assumptions in the description of mixture. What does ideal mixing imply in terms of our description of a thermodynamic system? It implies neglecting the attractive and repulsive forces that cause deviations from ideal mixing and that are represented by the excess terms: excess volume, excess entropy, and consequently excess Gibbs energy, which are all neglected, all placed equal to zero by assuming ideal behavior. But if the excess Gibbs energy is zero, its derivative is also zero, implying that the activity coefficient takes the value of 1, and consequently activity and mole fraction coincide. That's the origin and meaning of some simplified approaches that are often used and unfortunately sometimes abused in the literature. One relevant ideal simplification is Henry's law. Henry's law deals with multi-component gas-liquid equilibrium, and it says that in ideal conditions and at constant pressure and temperature, the amount of solute dissolved is proportional to its partial pressure in the gas phase. Here is a new exercise. As for the previous ones, you can either try to do it or skip it. In both cases, you will see the solution in the following. The exercise is this one. Based on the statement above, derive Henry's law. My suggestion is simple. Just start from the gas-liquid equilibrium equation in terms of fugacities. Press pause now if you are doing the exercise. Okay. In order to derive Henry's law, let's analyze its statement in light of the general equilibrium equation reported here. First, Henry's law refers to ideal conditions, thus to the case where the activity coefficient in the liquid phase and the fugacity coefficient in the gas phase are both equal to 1. With such an assumption, the equilibrium equation reduces to its ideal form reported here, from which we can explicit the mole fraction of the solute, that is, the component that dissolves in the liquid. Furthermore, Henry's law refers to constant pressure and temperature. We have analyzed in lesson 6 the reference fugacity of dissolved components and have seen that in general, and in the modeling that we have developed so far, the reference fugacity is a function of pressure and temperature. Thus, if pressure and temperature are constant, the reference fugacity is also constant, and so is its inverse. We can therefore treat the inverse of the reference fugacity as a constant, kh, in the equation at the bottom. By substituting, the amount of solute turns out to be given by a constant times its partial pressure in the gas phase. That's Henry's law, which is nothing else than an ideal form of the general equilibrium equation. The constant of proportionality between the solute and its partial pressure, kh, is called the Henry's constant, and it coincides with the inverse of the reference fugacity of the dissolved volatile, which takes a constant value at constant pressure temperature conditions. The attractiveness of the Henry's law is clear. Assume that we know the solubility of water in a given silicate melt, and assume Henry's law behavior. That is, 1, assume ideal behavior for the gas and the liquid phases, and 2, refer to fixed pressure temperature conditions. In such a case, we simply draw a straight line from water solubility to the origin of the axis in this diagram, and we read along that line the amount of dissolved water for any partial pressure of water in the gas phase, no matter what other volatile components make up the gas phase or dissolve in the liquid phase. While the advantages of adopting the Henry's law are clearly evident, the validity of the approximation is unfortunately restricted to conditions which are irrelevant for most applications when studying natural magmas. This figure shows that clearly. Here we see computations of water plus carbon dioxide saturation made with SolveCAD, the real multi-component thermodynamic model that embeds all of the equations that we have developed so far and those that we will continue to develop in this training module. The results are shown in a way that for both diagrams, which refer to 2 different silicate melt compositions, the black diagonal line corresponds to Henryan behavior. The blue lines refer to water, and the red lines to carbon dioxide. The closer the red and blue lines are to the diagonal black line, the better the Henryan law behaves. The closer we are to Henryan behavior. We see that in all cases, Henryan behavior is a reasonable approximation of the real behavior only for the lowest pressure employed, which is 1 megapascal or 10 bars. At 10 megapascals or 100 bars, as little as very few hundred meters below the Earth's surface, the deviations from Henryan behavior are already substantial. At larger depths, typical of magma in volcanic systems, the behavior deviates enormously from the simple Henryan approximation. At such conditions, a Henryan approximation, that is, the assumption of ideal behavior, results in equilibrium conditions which hold little or no relationships with those effectively characterizing the magma. There is a reason why we employ real thermodynamics, and that reason is clear from this figure. Ideal simplifications are largely inappropriate for practically the entire range of conditions of interest for magmatic and volcanic processes. Well, we have progressed substantially. We have seen in this lesson that in order to compute the activity coefficient of dissolved volatiles, we need to start from the excess Gibbs energy of the silicate melt where the volatiles get dissolved. By partial differentiation of the excess Gibbs energy with respect to the number of moles of each volatile, we obtain the corresponding activity coefficient. The definition of an expression for the excess Gibbs energy is therefore the last step for completing our fully real multi-component gas silicate melt equilibrium model. In the next lesson, we will see how to model the excess Gibbs energy of a mixture, and in particular of silicate melts. After that, we will be ready to use the model, make calculations, and explore multi-component water and carbon dioxide saturation in silicate melts. See you there.